Hi, welcome back. Okay, we talked about precision and accuracy in the last video. So we have two tools to express to people the sophistication and precision of our measurements. The scientific notation is one of those tools, and significant figures or significant digits is the other tool. So here's some very good memes on that. People get confused with this. It's not something that's intuitive, and it takes practice. But we're going to start with something that I meant to put on the last video, but the video was running long, so I dumped out of it. Once you know the once you know the correct value, you can take a look at the data you got and calculate what's called a percent error. Now, with percent error, there's an absolute value in here because we don't care about the direction of the error. We just care about the magnitude of the error. How close to the average are we? How close to the accepted value are we? So when they say lab value in this formula, they mean what you got from your many data trials, not from one data trial, but from many data trials. And then we're going to find the difference between that and the real value. And when I say real value, I mean the people who have done thousands of experiments. So like for instance, in the next example, we're going to talk about Merck Pharmaceuticals. Well, Merck does thousands of experiments, not a few experiments. So we're going to accept the values that they publish as being the correct values. But do understand, they're still working things out too. As time goes on and technology gets better, they may redo those experiments. And the values that they report today may be slightly different than the values that they report in 10 years. Oopsie poopsie. Let's go back to this. Percent error, lab value minus accepted value divided by accepted value times 100%. And then we're going to do this problem. So I'm going to copy it and paste it. Okay, so this is going to be a formula-based problem, not a conversion factor. So we have to start with our formula. Our formula is percent error is equal to absolute value of the lab value minus the accepted value, and we're going to put that over the accepted value. And just like with all percents, we're going to take that answer and multiply it by 100%. So our units should cancel, and then our units should be percent when we're done. All right, so we take a look at this problem. It says you measure the density of a metal. Again, after many trials, you come up with 4.57 grams per milliliter. We look at the Merck index, which reports the density of that metal at 5.06 grams per milliliter. What's the percent error? And you're like, oh my gosh, Mr. Burnett, put a ton of these on the test because this is easy. All right, do we have to solve for a variable here? And the answer is no. We already have it solved for percent error. That's what we're trying to find. So we can just substitute in the values. Now, they don't tell us the identity of the metal. So we can put in the number, the unit, but we do not have to put in the label of the chemical because we do not know it. 4.57 grams per milliliter minus 5.06 grams per milliliter. And again, we're going to take the absolute value of that and divide it by the accepted value, 5.06 grams per milliliter. And remember to multiply that by 100%. Because in your documentation, if you leave that out, you lose partial credit. So 4.57 minus 5.06, we get negative 0.49, but we're going to take the absolute value of that. So we get 0.49 grams per mil over 5.06. Now, you don't have to show this. Once you showed the substitution, you could just work out the answer in the calculator. I did the subtotal here because I want to show you what happens with the significant digits. So when we subtracted, we got 0.49. We divide by 0.506, and then we're going to multiply that by 100, and we get 9.6837944466. We, of course, are not going to include all of those numbers. We're going to focus on the first two because we only have 2 digits in our numerator. We have 3 significant digits in our denominator. Now, we haven't discussed sig figs yet, so don't get upset. It's going to be in this video. So what I'm going to do is I'm going to take that 9.6837944466 and I'm going to round it to 2 digits. 9.7 percent. That is my percent error. And on free response, I make sure that I box the answer. Easy. Put a bunch of these on the test. Okay, we said we have two tools to express precision. One of them is scientific notation. A lot of people say, well, scientific notation is a way of making long numbers short. Well, that's not always the case. I mean, we can have a number like 1, and writing 1 as 1 times 10 to the 0 to put it in exponential notation doesn't make it any shorter. It's actually designed to show precision, and it's set up to show where your estimated digit is in your measurement. So in scientific notation, you learned this in middle school. It's a lot like exponential notation, except when we're dealing with the coefficient in the scientific notation, there are some limits. Same thing with the exponent, so let's discuss what those limits are. First thing, the coefficient has to be a number in the ones column. In other words, you can have a scientific number like 3.7 times 10 to the 8th meters. But you cannot have 37 times 10 to the 7th meters. Now, numerically, they mean the same thing, but that's not how scientific notation is done. And the reason why is we want to show the precision. We're saying that the 3 is a known digit, but this number after the decimal point, that's my estimated value when I made the measurement. So that's my estimated digit. And if you start using numbers like 10, 130 for your coefficients, then you start to muddy the waters, which means you're not going to be able to tell where the precision is, because zeros are kind of tricky. Zeros can show precision, but sometimes they're just algebraic placeholders, and we'll get to that in just a moment. So to show precision, we put things in scientific notation based upon the coefficient. But the coefficient has to be a number between 1 and 9, and then a decimal point, and then however many digits you need to put after the decimal point to show the precision. The exponents are going to be whole numbers. They can be positive or negative. And at this point, they expect that in middle school you learned how to convert from exponential notation to an Arabic Hindu number, or to convert from the Arabic number to scientific notation. I had a course, it actually called Arabic Hindu. I don't know why the Hindu part got cut out of it. I guess because it was shorter. But everybody always says Arabic number. It's actually Arabic Hindu. Converting from number to scientific notation, and then I'm going to show you how to deal with calculations for scientific notation in units. So, again, review of middle school for the first 2 topics. So this should not be hard. All right, if we go from scientific notation to a Arabic number. Let's say they give you 3.76 times 10 to the 4th, and we'll make that candelas because it has to have a unit. If it's scientific notation, it's a measurement, so it has to have a unit. And we're going to convert that. Now, the 10 to the 4th represents 10,000, so 10,000 times 3.76 would give you 37,600, which is the answer. But remember I said I didn't want you shifting the decimal point when we did metric conversions? Here you could shift the decimal point if you want. I always try to remember when it's a positive exponent, and you can do this however you want. You don't have to use my technique. But since this is 10 times 10 raised to the 4th, it's not going to be 4 digits. It's actually going to be 5 digits. So we're going to have 5 digits, of which the first 3 are going to be 3, 7, 6. And then we put in the rest of our digits to have a total of 5. So this is going to be 37,600. In science, we usually don't put in a comma. I'm going to put it here because I made them so close. What you do is you put a space for every 3 numbers related to the decimal point. So really it should be written as 37,600 candela. If you have a negative exponent, like 6.1 times 10 to the minus 6 meters, then this negative exponent tells you the column with which you should start writing this coefficient. Let me show you. So this is going to be to the right of the decimal. We start with a decimal place, and we go 1, 2, 3, 4, 5, and in the 6th column, right? That exponent, -6. In the sixth column, we write 6, and then we write 1, and then meters. Now, you can do it the way the book asks you to do it. You can shift the decimal place like some of you like to do. That's fine, because we're not going to look at the work. We're only going to look at your results when it comes to this. Now, I'm very process-oriented, but we don't need to see a process for this thing that you learned in middle school math. All right, to go from the number to the exponent. Suppose we have a number less than 1. So 1, 2, 3, and then we'll do 1, 6, and let's make that centiseconds. And I want to convert that to scientific notation. Again, you could shift the decimal, but the way I deal with numbers less than 1 is I say, okay, my first non-zero digit is in the first column to the right of the decimal. That means my exponent is going to be 10 to the minus 1. And then that means that I am going to start writing my coefficient as 1.2316. Again, if you were taught to shift the decimal, this is the 6th time I've said it, you're welcome to shift the decimal if that explanation didn't help you. If I'm trying to offer a different perspective for doing it, but like I said, I don't care as long as you get the right answer. And for this one, if we have 4, 5, 0, 0, 0, 0, 0, 0, 0, 0, and let's make that micrograms. The way I would do this is I would say, look, how many digits do I have? I know I'm going to be multiplying this by 10 to the whatever power. So we have 3, 6, 9 digits, and then I don't count the last one because we're multiplying by 10. That means I have 9 digits to the left of the decimal besides the first digit. So that's going to be 10 raised to the 9th power. And then I write the 4.5. Now, these zeros, are they part of the precision? And the answer is we don't know. We don't know with zeros, and I'm going to talk about that in the next section when we talk about sig figs. Don't forget to put in your unit, or else you'll lose partial credit. Last thing, doing calculations. Now, doing calculations, you can either use a calculator or you can use the law of logs to do this. I prefer to use a calculator because your calculator is designed to show you scientific notation. I'm going to bring up an example of a scientific calculator from the internet. Let's see what we got here. We got my memes. We got normal distribution from the last video. Let's go. Here we go. That's not it. Sorry, I didn't already have this up in the slideshow. Don't know why. Here we go. Alright, so this would be a typical scientific calculator. Let's see if I can copy and paste that. Ugh, I can't. Alright, so I'm just going to use it the way it is. Alright, so suppose we wanted to do something like multiply two scientific notation digits together. Let's say we had this problem. We have, see if it'll let me write on here. It will not. Wonderful. Let's say we wanted to do, I'll go back to the slideshow. Oh my goodness, sometimes things don't work out when you're in a hurry. Let's say we had to do the following calculation. We have 3.6 times 10 to the minus 5 meters over 1.4 times 10 to the 8th seconds. We want to calculate how many meters per second that is. The way the scientific calculator works, and it's different for each company, so you're going to have to find your key, is it's set on what's called a macro. A macro means that there are two parts. You enter the first part, you hit the function key, and then it's asking you for a second part to complete the problem. So our first value here is 3.6 times 10 to the minus 5. I'm going to put that in using scientific notation. So I put in 3.6, which is the coefficient. EE is the key for TI calculators. You also could have a an EXP key if you're dealing with Casio, and then there's a couple other ones too. You may have to read the directions to your calculator to be able to find the function key. But you hit the function key, EE, and what that says is it's now waiting for your exponent. And we said the exponent here was -5, so I'm going to type in -5, and it did not work because the internet is a piece of crap. Okay. Maybe I'm doing something wrong. I don't know, it looks like I got an error when I hit EE. Alright, I'm going to do it this way then. I'm going to type in a 3, and then a decimal point, and then a 6. That's my coefficient. And then you have to hit the function key on the calculator. On some calculators, it's EE. On Casio, it's EXP. On some, it's X10 to the N. The one key you don't want to hit, though, and I'll explain why later, is to use the 10 to the X key. So we're going to hit 3.6 exponential function, and then I'm going to type in plus minus for negative, and then a 5. And what I should get is something like this on my calculator. 3.6, and it's probably going to say E, because that's computer jargon for exponential notation, and then it'll say -5. So that's the computer version of 3.6 times 10 to the minus 5. To continue with the problem, what I'm going to do, let's get rid of this so we can simplify it, is I'm then going to hit the divided by key. And then I'm going to enter another scientific digit. This time I'm going to enter 1.4. And you should try this on your calculator after seeing this. The exponential function key, and then 8. And what that's going to do is that's going to divide the 3.6 e to the minus 5 by 1.4 e to the 8th. And when I do that, I'm going to put it into my Casio. 3.6 exponential -5 divided by 1.4 exponential 8. And I get 2.571428571 times 10 to the minus 13. So 2.6 times 10 to the minus 13 meters per second. I'm going to try another one. Suppose I had this. I'm going to do 2.17 times 10 to the minus 3 kilograms per meter squared, whatever that is. And I'm going to multiply it by 1.184 times 10 to the 4th meters per second. And then I'm going to divide it by 1.4 times 10 to the 6th. Let's do kilograms. And then let's do 3.6 times 10 to the minus 12. And we'll make this kilograms per meter seconds. Okay, what is this value? Alright, if we're doing the law of logs here, we could multiply the numerator coefficients, 2.17 times 1.184, and then divide that by 1.4, and then divide that again by 3.6. And then we could add -3 to 4, and then subtract the exponent 6, and subtract the other exponent, -12, and do it that way. I'm supposed to teach you that way. I just did. I don't recommend that anybody do it that way. I would use the calculator because the calculator has a function in it. We're going to be looking for that either, actually on some TI calculators, it's an E button above their numeric pad, or it could be an EE button for the key, EXP, and then on some calculators it's times 10 to the N. This is tough because this is the sort of class where I would go around the room and I would check to make sure everybody's doing their function keys correctly. Again, you may have to go online and type the instructions for your calculator on how to do this exponential notation. But you're looking for that function key because, again, you put in the coefficient, you hit the function key, and then you type in the exponent. And the calculator takes care of all the rest. Now, right now, you're going to be resistant to wanting to use it because it's a little awkward for you. If you use the 10 to the X key, then you run the risk of being the victim of algebraic operators. In algebraic operations, the computer is programmed to do exponents first. So let's say you're typing all this in, 2.17 times 10 to the negative 3 times 1.184 divided by, and then we'll have to use parentheses, 1.4 times 10 to the 6, blah, blah, blah. When you get to the negative 12, the computer, if you use 10 to the x, the computer is going to do that first, which is going to put that up in the numerator. The computer doesn't speak English, it speaks computer. So you have to manipulate this in a way that the computer can understand what it is that you're entering, because it doesn't have eyes. And that's where this function key comes in. So if I was doing this, and follow along, I'm going to do 2.17 EE negative 3 times 1.184 EE 4 divided by 1.4 EE 6. Every time I hit EE, I'm using that function. The function's saying, all right, you gave me the coefficient, now put in the exponent. I'm going to hit divided by again for the last one. Why? Because the computer doesn't know that you're multiplying the two values in the denominator together, and it's going to follow algebraic operators. If you don't use parentheses correctly, you're going to mess the computer up. So my advice to students is, anytime a number is in the numerator, you multiply. Anytime a number is in the denominator, you divide. So I'm going to do the first number times the second number divided by 1.4 times 10 to the 6th divided by 3.16 times 10 to the minus 12, and I'm going to get the right answer. So let me put that last number in. 3.6 exponential negative 12, and then I hit equals, and I get, I am old. It is hard for me to read what I get, but it looks like I have 5,097,777.78. And I'm only going to use two of those digits, so I'm going to do 5,100,000. Again, we'll talk about how I was able to round that and get it down to two digits in the next section. The other thing students struggle with is dealing with these units. Treat units the way you would if they were variables in algebra. So I'm going to take the first one, kilograms over meters squared, and I'm going to multiply it by the second number, meters over second. The unit in the third one is in the denominator. So you're going to divide. When you divide, that's the same as multiplying by the reciprocal. So if this is kilograms over 1, I'm going to write in 1 over kilograms. And then for the last one, again, dividing by kilograms over meter seconds is the same as multiplying by the reciprocal. So I'm going to move meters per second, kilograms up there. Now I cancel out my units as best that I can. And that's all I'm left with is kilograms to the negative 1 power, or you can just write 1 over kilogram if you prefer that. But most of the time in science, we will write that that is kilogram to the negative 1 power. So there's my value and my unit. So you really have to go through the textbook, and they give a description of how to use exponential notation on the calculator. Right now, it's going to seem slow, but when you practice it, you will get faster and faster at it, and it will become second nature. Again, caution, if you're going to use your calculator to do scientific notation, unless you're really good at putting in the parentheses correctly, avoid using the 10 to the x function key, because if you have a negative exponent in the denominator and you use the 10 to the x function key, the calculator is going to think you meant to put it in the numerator, and you will get the wrong answer. All right, sig figs themselves. Sig figs represent our error in our measurement. Remember we said that we have an estimated digit at the end? Well, significant figures will give us an indication of where that measurement was. So again, what sig figs are is a reflection of how much precision you had in the instrument. When we're using sig figs, we only use them to things that have a measured unit. Counted things are considered infinitely significant. In other words, if I have 5 books on my table The precision is infinite because anybody who comes in and counts those books is going to get the same exact number every time, provided that they know how to count. So things that can be counted do not have significant digits. They are infinitely significant. Now, you have to be able to count them. So if you talk about things like geological time being 20 million years ago, for instance, that actually has significant figures in the measurement because nobody can actually go back and count 20 million years. You're getting that from measuring probably carbon-14 data or some other aging type of data, and so therefore it's actually a measured value. The rules are, when you write a value in a measurement, any non-zero digit is considered significant. In other words, non-zero numbers automatically are part of the precision of the instrument. The problem is with zeros. Zeros can act like part of the precision. Like if I step on a bathroom scale and it says 290.0 pounds, we know that that 0.0 is part of the precision. It was part of the sophistication of the weighing scale. It's where my estimated digit is. But if I was to say, for instance, I had 8 million grams of something, well, with those zeros, are they estimated? Are they just holding a place so that my first number is in the millions column? Or did our scale actually estimate to the plus or minus 10,000 grams? Or did it estimate to the plus or minus 1 gram? We can't tell with zeros. Zeros are vague. So exponential notation removes the vagueness from zeros, which is why we use it. All right, so all non-zero numbers are significant. For instance, if I had a measurement of 4.67 grams, I would say that this measurement has 3 significant figures in it. Now, counting up the number of significant figures is important because when we do a calculation, it's going to give us a bearing on how many of those decimal places we should use when we do the calculation. For instance, let's say we're doing density. If we take a Walmart bathroom scale and we weigh something at 2 pounds, and then we take a Walmart bucket and we find that the water in the bucket is 3 liters, that doesn't mean our density is 0.66666666666666 going on forever pounds per liter. There's some limitation in the sophistication of that equipment. And to sit there and use a Walmart bathroom scale in a household bucket and then sit there and tell somebody that you got the density of the object to 12 decimal places would be ridiculous. Wouldn't it be more realistic to tell people that your density was 0.7 pounds per liter? Because when you see a number like 0.666666666, you think of sophistication. You think that the tools must have been highly precise. But in reality, we got that number because of an algebraic fluke. We had a non-terminal, non-repeating decimal because of the fact that we divided 2 by 3. It had nothing to do with the precision. So it's a lot more responsible to report our data as 0.7 because it is similar to the values that we used when we calculated the density. So there are certain rules for when you multiply and divide. There's certain rules for sig figs when you add and subtract, but the first thing you have to be able to do is to look at a measured value and count up the number of sig figs. So anyway, any non-zero number is significant. Great. Trailing zeros to the left of the decimal are not significant. So that means that if I have a number like 35 million hours, then we would say that only these 2 are significant digits, sig figs. So we have 2 sig figs here. Now, could these be part of the precision? Yeah, but we don't know. It's vague. We don't know if it was part of the instrument or if it's just holding the place so that we wind up in the millions and 10 millions column with the 5 and the 3. To avoid that, what you would do is put this in scientific notation. Let's say, sorry, let me go back to that slide. Let's say all of these values were significant. So we would write it as 3.500000000 hours. Why? It's just like a bathroom scale. If I step on a scale and it says 290.0, And then I step on a different scale and it says 290.0000. Which scale has more precision? The one with the zeros after the decimal place. So what we do is we take these vague zeros that are to the left of the decimal place. Oh, I'm sorry, I didn't write the correct value here. Times 10 to the 7 hours. I'm sorry, 3.5000000 times 10 to the 7th hours. So by converting it to scientific notation, it's the same value, but now all of these zeros are to the right of the decimal place, and we know they're part of the precision. So when we have zeros to the right of the decimal place, they count as sig figs. When they're to the left of the decimal place, they are vague. So we would say that this value here has a total of 8 sig figs. Next rule, leading zeros are not significant. Leading means that they come before a non-zero number. So if you have something like this, 0.0054 grams, then we would say only these two are significant. These zeros are vague. Now that does change slightly in Rule 5. If you have zeros that are trapped in between non-zero numbers, go ahead and count them towards your significant figures. Like for instance, if you have 304.6005, let's do millimeters, then we know that the 3, the 4, the 6, and the 5 are part of our significant digits. But because these zeros are trapped in between non-zero numbers, they also become part of the precision. So this actually has 7 significant figures, all 7. Now, calculations should always be expressed based upon your least precise entity. So if we were to measure density with a scale that went down to 6 decimal places for grams, but then we use a Walmart bucket, a plastic bucket, for the volume, our density measurement isn't going to be very precise. You throw the precision off by making one of the instruments unsophisticated. So our calculations have to bear that out. But before I get to that, I'm going to do Rule 7, and then we'll do the calculations in Rule 8. Exact numbers are infinitely significant. How do we know an exact number? An exact number, they use the term 1. So if they say 1 meter equals 1,000 millimeters, that's considered infinite sig figs. It is exactly precise. And then the rule is that addition and subtraction have different rules for dealing with sig figs than multiplication and division. I'm going to go over that in a moment. And we already know that the precision of the instrument, the last digit, is an estimated digit, and that the precision of that instrument is based on that estimated digit. That was the last video. All right. And then I'm going to end with showing you how to round. So I'm going to try to do this quickly. I'll do one example of each. Let's say, for instance, we're doing a density calculation. And in our density, we measure the mass to be 8.6178 grams. And then we measure the volume to be 430 milliliters. What's the density? Well, density is mass divided by volume. And the rule is, when you multiply or divide, your final answer should have the same number of sig figs as your least precise measurement. So let's see what we have here. All right, for the mass, how many sig figs? Well, they're all significant because they're all non-zero digits. So we would say the mass has 5 sig figs. And the volume, this 0 is to the left of the decimal, so it is vague. So only these 2 digits count for sig figs. So this volume measurement, even though it has 3 digits, only 2 of them are considered significant. The other one is a placeholder. Now that placeholder is important. We can't just say the volume is 43. 43 milliliters is very different than 430 milliliters. But we're saying, for the sake of calculation, we want our final answer to only have 2 of the digits be significant. So here's how you do it. You substitute in, and then you get out your handy dandy calculator and you do 8.6178 divided by 430, and you get 0.0004139.5 grams per milliliter. Now we know that all of those digits should not be part of the answer. That our precision was based upon having two significant digits. So in order to do that, I'm going to rewrite this as scientific notation. I'm going to do 2.0 times 10 to the minus 2 grams per milliliter. Now, how do I know that's two significant digits? Look at my coefficient. I got a non-zero number, and then the 0 is to the right of the decimal. Anytime the 0 is to the right of the decimal, as long as it's not a leading 0 like this, then it is considered part of the precision. All right, let's try another one. Suppose we get the mass to be 40.06 grams, and then the volume is, let's do 23 milliliters. So again, when we do sig figs for this, the mass has 4 sig figs, and the volume only has 2 sig figs. So how many sig figs should be in our final answer? Well, it should be 2, the one with the least precision. So now we're going to substitute in for density. 40.06 grams, 23 milliliters, and we get 40.06 divided by 23 is 1.74173913, and we know it is just plain wrong to have all those decimal places. So we need two significant digits. So here's what you do. You find the first two significant digits, and then you base your rounding off of the third digit, and then you completely ignore the rest. So my final answer is, I'm going to round down because the third digit is a 4. So this comes out to be 1.7 grams per milliliter for my density. What if you get an answer like the density comes out to be 20 grams per milliliter, and they want you to express this in 1 sig fig? Let's say we do our calculation and we find we need to answer this in 1 sig fig. That's another case where you're going to have to convert this to scientific notation. So I'm going to rewrite this as 2 times 10 to the 1 grams per milliliter, because again, it's your coefficient that determines the number of sig figs when you're doing scientific notation. If I left it as 20, this 0 is a placeholder, and then I'm only answering with 1. Oh, I screwed that up. I'm sorry, it was already 1 sig fig. Wow, this is a bad night for me. Let's say I wanted 2 sig figs. I'm sorry about that. Then I should write this as 2.0 times 10 to the 1. If I leave it as 20, the 0 is vague, and this would be construed as only 1 sig fig. So if I need to write 20 using 2 sig figs, I'm going to convert it to scientific notation to give me 2.0 times 10 to the 1. Sorry about that. All right, last calculation. What if we're dealing with addition or subtraction? With addition and subtraction, you add and subtract them normally, and then you look for the least precise column of commonality. Let me show you what I mean. If we take 43.6 grams and add it to 2.17 grams, and then we're going to add that to 133.5 grams, we're going to add them up normally. So we get 7, 12, 9, 7, 179.72 grams. However, we have to go by the least precise measurement. So in the first measurement, our most precise digit is only in the tens column. In our second, our most precise digit is going to be in the hundreds column, and the third is going to be in the tens column. So you go by the one with the least precision. So we're going to limit our answer to the tens column. They all share that column in common. So I'm going to take my value and I'm going to cut it off in the tens column. And then I'm going to look at the 100th column and do my rounding. So I'm going to round this up. So this actually comes out to be 179.3 grams. All right, try this one because this one's a little tricky, and then I'm going to end the video. What if we had 46.205 milliliters, and we're going to add that to 123 milliliters, And then we're going to add that to 1,000. I'm sorry, let's make it 2,000. 2,100 milliliters. What is the answer? Okay, so we're going to add this like we normally would. So we get 2,269.205 milliliters. And then we look at the columns that they have in common. Do all three have a value in the 1,000ths column? And the answer is no, so we can't have our answer in the 1,000ths column. Do all three of them have digits in the 100ths column? Significant digits, and the answer is no. Do all three of them have significant digits in the tenths column? No, so that's out. Do all three of them have digits that are significant in the ones column? And the answer is no. That's a placeholder. Do all three of them have significant digits in the tens column? And the answer is no. That's a placeholder. Now, once you get past this, and there's no longer a number here, then only these two columns have to have non-zero numbers. So we're going to have to cut off our value in the 100ths column right here. So we're going to take a look at the third number past it, or the number past it rather, for rounding purposes. And we're going to write 2,300 milliliters. Now, you can't just round it and write 23. Again, 23 is very different than 2,300. These become zero placeholders, and we no longer need anything past the decimal. Let's end on a make. Let's end on an easier one, because that's complicated. That's AP level. Let's try this. What if we did 36.5 grams, and we're going to subtract 8.118 grams? What is the correct answer with sig figs? Please give it a try. I'll pause and I'll wait. I'm back. So I'm going to subtract this the way I normally would. So we get 28.382 grams. And then we say, well, where's the column that they both share where they get the most precision? And that's right here in the tens column. So my answer has to end in the tenths column. And then I use the 8 for rounding. And I get 28.4 grams. That's the correct answer. All right. Thank you very much. Catch you on the next video.